Let's talk about the idea of standard deviation and what are called the 5 golden rules for reporting results. So let's imagine we have a student who makes several measurements of the period of an oscillation of, say, a mass on a spring. So here's the data they have. What should this student report for her measurement? Well, of course, we're going to be taking an average to start with. So we would take the average of these values and we would get 10 seconds or 10.00 seconds or something like this. We're not really sure how many digits to include, how many significant digits to include at the moment. But what do we do about uncertainty? So we have a measurement. Whenever we have a measurement, we should report an uncertainty associated with that. So if we have a set of data like this, a natural thing to think about for the spread in the data or the uncertainty in the data is what's called the standard deviation. And so for the standard deviation, we take the difference between any individual data point and the average value. We square that, and we add that up for all of the data points. We divide by n minus 1 of the number of data points. N minus 1 is there instead of n because you have to have 2 data points in order to get a standard deviation, really. And then we just take the square root of that for the standard deviation. So that's the mathematical definition of the standard deviation, but what it's trying to tell you is it's trying to tell you something about the width of the distribution of your measurements. So I've plotted here the period measurements, but in bins, where we're counting the number of occurrences of the period in any particular bin. And we can see that this distribution has a little bit of a width. Well, there's not much of a distribution here, but it's centered somewhere around 10, and there is a bit of a width. And the idea of the standard deviation is that 68% about of measurements should lie within the average value plus or minus the standard deviation. And we can see we've got 3 out of the 5 that are lying within plus or minus the standard deviation as shown here on the plot, and so that's about 60%, so it's pretty close. The standard deviation is telling you the uncertainty of any single measurement. So if you're going to make a single measurement, it would tell you what you should expect for the uncertainty. For this student's data, we find a standard deviation of 1.232883 seconds. Again, we need to talk a little bit about how many significant digits to include here, but let's just include a bunch of them for right now. And so that would be the uncertainty in any particular measurement. We can see that our values are centered around 10 with an uncertainty about 1 point something, 1.2-ish is kind of the spread of the data. Now you can make these calculations in Excel as well as doing them by hand. So let's talk a little bit about how you do them in Excel. So in Excel, here I have that same data, the trial numbers, and I have the period. And I want to calculate the average, the standard deviation, and well, we'll talk about the standard deviation of the mean in just a little bit. So if I want to calculate the average, I'll just do the usual way of calculating average in Excel. I write equals for a formula, and then I'll just call average, and then I can select my data, close the parentheses, and hit enter, and it calculates my average. So as I saw before, it's 10, 10.00, something like this. If I want to calculate the standard deviation, as the note here suggests, I'm going to use this particular function for standard deviation. The reason that I'm being very specific here is there's lots of different definitions of standard deviation in Excel, depending on things you want to do. We want to use the version stdev, standard deviation, .s for our data. So I'll write equals stdev .s, open parentheses, and then I'll select my data, drag and select, close parentheses, hit enter, and it calculates my standard deviation with the result that I had before, 1.23288, and then 3 if we round that last digit. So the problem with the standard deviation, though, is that the standard deviation doesn't tell you how well you have made a particular measurement. So more data, more measurements, doesn't necessarily mean a smaller standard deviation. Let's say instead of 5 data points, I measure now 100 data points of the period, and I get the exactly same average, so I get 10 seconds for my average period, and I get a spread of data, and the spread of data will in fact still be the same, or typically is going to be the same, because any individual measurement has the same uncertainty associated with it. And so I have this spread of data now. And so if I were to report the standard deviation as the uncertainty in my measurement, I think that would be a underestimating the degree to which I know the period now. I've made more measurements, and so I should be more certain that the average value of the period is somewhere around 10. But the standard deviation won't show that. It's just taking the average deviation of all of our data points from the average itself. So we need a new quantity, and this new quantity is called the standard deviation of the mean. So not to be confused with the standard deviation of the mean itself. And this quantity is characterizing the reliability of your mean value, or of the average value. So the definition is you take the standard deviation and then you divide by the square root of n, the number of data points. That's really important because if you have more measurements, more data points, then even if sigma stays the same, even if you have the same uncertainty on any individual measurement, you're now getting more and more precise on your average measurement. So what does this look like for the data we have up above? So if we only had 5 data points, then I would have had a standard deviation of the mean of 0.55 seconds. But with 100 data points, my standard deviation of the mean goes down to 0.12 seconds. So it definitely helps me be more precise about characterizing the average value that I've measured. Namely, it's telling me that I know the average value much better now. So notice that that is significantly smaller, but it doesn't decrease by n, it decreases by square root of n. And so at some point, making more measurements doesn't really help you. Somewhere around 100 is about where you're going to get much benefit from the standard deviation of the mean. So now that I've talked about the average value, the standard deviation, and the standard deviation of the mean, what value should we report for the measurement of the period of this particular mass on a spring? Well, we're going to follow what are called the 5 golden rules for reporting results. So the rules are as follows. So we're going to report the average value, because that's the best estimate of a parameter that's been measured. The uncertainty we're going to report is given by the standard deviation and the mean. We're going to quote that uncertainty to only one significant figure. Unless you have something of order 10,000 data points, then you need to start worrying about including more than one sig fig in your standard deviation of the mean. But for all intents and purposes, one significant figure in the uncertainty will be just fine. Then you're going to match the decimal places in the mean to the uncertainty. So, for example, I wouldn't write in this fourth circle here 9.80 plus or minus 0.1. I want to match the decimal points, so I'll have 9.8 plus or minus 0.1. And then, of course, I should always include units whenever I'm reporting a result. So what does that look like for our data? So the data that our student had, we had an average value of 10.00 seconds. We had these values for our standard deviation and the standard deviation of the mean for our 5 data points. And so the student should ultimately report a result of 10.0 plus or minus 0.6 seconds, where I rounded the 0.55 up to 0.6. Notice the features of the 5 golden rules here. I'm reporting the average. The uncertainty I'm reporting is the standard deviation of the mean, reduced down to one significant figure. I'm matching the decimal point on the average to the decimal of the standard deviation of the mean. And I made sure that I had units. Okay, so this is how you would calculate standard deviation and report results of a measurement.